Hi everybody, welcome to another lecture of complex variables. It's about time we introduced a third form of notation for complex numbers. We have rectangular coordinates where a complex number is equal to a real number plus an imaginary number. AX plus, A plus BI or X plus YI. Real number A plus imaginary number BI. Put them together, we get a complex number. We can also represent the complex numbers in polar form. The modulus R times, in parentheses, cosine of theta plus I sine of theta. Now we're going to look at a third way that we can represent complex numbers. And actually it's fairly closely related to polar coordinates. Now, just to set the tone for the conversation and to give us some background information, remember from Calculus 2 the Taylor series expansions for some well-known functions. For any real number x, the cosine of x is equal to the infinite series 1 minus x squared over 2 plus x squared over 4 minus x squared over 6 plus x. Let me try that again. I think we only have one x squared here. 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10 over 10 factorial. It's an infinite series. We can write it like this. The sum from I equals, I'm not sure what. Let's see. I guess 0 to infinity. And instead of I, let me use n. N equals 0 to infinity. So I guess if this pattern extends backward, this would be x to the 0 over 0 factorial. So when n is 0, we have x to the something, well, we have x to the 0 over 0 factorial. When x is 1, we have x squared over 2 factorial. When x is 2, we have x to the 4th over 4 factorial. So I guess the pattern is this. Whatever n is equal to, the exponent is twice what n is. The exponent is 2n, and the denominator is 2n quantity factorial. So we have x to the 2n over 2n quantity factorial. Let's see if that's right now. If n equals 0, we have x to the 2 times 0 is x to the 0, which is 1, over 2 times 0 factorial, that's 0 factorial, which is 1. So we have 1 over 1. Yeah, that works. When n is 1, we have x to the 2 times 1, x squared, over 2 times 1, 2 factorial. Yeah, that works. I guess the only thing that we haven't accounted for here are the plus and minus signs. And the plus and minus signs alternate. So let's see. I think the way we do that is we take -1 and we have to raise it to a power. Let me move this a little bit further right. Okay, we have to raise -1 to a power. When n is 0, if we have -1 to the n power, that's -1 to the 0, which is +1. It works for n equals 0. If n is 1, we have -1 to the 1 power, which is -1. Yeah, it seems to work. If n is 2, we have -1 to the 2 times 1 power. -1 squared is +1. Okay, I'm convinced. This is what the infinite series for cosine of x equals. The infinite series of sine of x is similar, except if you notice, cosine of x has the even powers of x. X to the 0, x squared, x to the 4th, x to the 6th. X to the even powers. The Taylor series expansion for sine of x has all of the odd powers. X to the 1st, x cubed, x to the 5th, x to the 7th. So apparently, we can write this as n equals 0 to infinity. And we have x to the odd powers. Well, let's see. Odd numbers are represented as 2 times n plus 1. Is that right? I think so. X to the 2n plus 1. And I'm going to guess 2x plus 1 factorial on the bottom. Let's see if we have it right. When n is 0, we have x to the 1st over 1 factorial, which is just x. Yeah. When x is 1, we have x to the 2 plus 1, or x cubed, over 3 factorial. Yep, I think that's going to do it. The only thing we need to do now is figure out what power to raise -1 to. And let's see, here it was -1 to the n. What's it going to be here? When n is 0, we want -1 to be raised to a power that makes it +1. When n is 0, we want a plus sign here. And when n is 1, we want a minus sign here. I'm thinking n plus 1. That's what I'm thinking. Let's see if it works. When n equals 0, we have -1 raised to the 1st. No, I don't think so. Maybe just n, huh? Let's see. When n is 0, we have -1 raised to the 0, which is 1. When n is 1, we have -1 raised to the 1st, which is -1. Okay. Hey, shame on me. I should have known that. So this is Taylor series for sine of x. Now another well-known function is e to the x. This is what the Taylor series expansion looks like. And this one has all of the powers of x, even and odd. And all of the terms are positive, so I don't have to worry about a sign changing -1 to a power. But when n is 0, I have x to the 0 over 0 factorial. I think so. When x is 1, I have x to the 1 over 1 factorial. When n is 2, I have x to the 2 over 2 factorial. When n is 3, I have x to the 3rd over 3 factorial. Okay, I'm convinced. I'm convinced that this is x to the n over n factorial. And again, let's check it out. When n is 0, we have x to the 0, which is 1, over 0 factorial, which is 1. 1 over 1 is 1. When n is 1, we have x to the first over 1 factorial, which is x over 1, or just x. Yeah. And when x is 2, we have x squared over 2 factorial, which is x squared over 2. And when n is 3, we have x cubed over 3 factorial. Yep. Okay. This is definitely the Taylor series expansion for e to the x. Now, let's try something. Let's let x equal I times theta. For x, we're going to plug in I times theta. And what that means is, every place over here where we see an x, we're going to put I times theta. So we're going to get 1 plus I times theta plus I times theta squared over 2 plus I times theta cubed over 3 factorial. Okay, put an I times theta in here for x. We're going to get I times theta to the 4th over 4 factorial. And put I theta in here for x. We're going to get I theta to the 5th over 5 factorial. Put it in here for x. We'll get I theta to the 6th over 6 factorial. Put it in here for x. I theta to the 7th over 7 factorial. Put it in here for x. We'll get I theta to the 8th over 8 factorial. And put it in here for x. We get I theta to the 9th over 9 factorial. And put it in here for x to the 10th. We get I theta to the 10th over 10 factorial. And then we get etc. factorial, or maybe etc. and then an exclamation mark, which means good grief, it's over. Okay. Now we do have this property of exponents that says that if we have a product raised to a power, that's the same as raising each factor individually to that power. So what this turns out to be is 1 plus I theta plus I squared theta squared over 2 plus I cubed theta cubed over 3 factorial plus I to the 4th theta to the 4th over 4 factorial. And then I to the 5th theta to the 5th over 5 factorial. I to the 6th theta to the 6th over 6 factorial. Plus I to the 7th theta to the 7th over 7 factorial. I to the 8th theta to the 8th over 8 factorial. Plus I to the 9th theta to the 9th over 9 factorial. And then I to the 10th theta to the 10th over 10 factorial. Believe it or not, there's a reason why I'm carrying this out so far. Let's see, I have 1 plus I theta. Now, what do we get when we square I? Isn't I the square root of -1? So if we square I, we're going to get -1. So this is going to be negative theta squared over 2. And if we cube I, isn't I cubed equal to I squared times I? But I squared is -1. So I cubed is I squared times I, or -1 times I. So we get negative I theta cubed over 3 factorial. And then I to the 4th. Well, I to the 4th is I squared times I squared. And I squared is -1. So this is -1 times -1, or +1. I to the 4th is +1. And we get theta to the 4th over 4 factorial. And I to the 5th, isn't that I to the 4th times I? But I to the 4th was +1. So I to the 5th is I to the 4th times I, or 1 times I. So this is just I times theta to the 5th over 5 factorial. And then here we have I to the 6th. But I to the 6th is I to the 4th times I squared. I to the 4th is 1, and I squared is -1. So this is just 1 times -1. And that will give us -1. So we have theta to the 6th over 6 factorial. And let's see, I to the 7th, that's I to the 4th times I cubed. And I to the 4th is 1. I cubed is -I. So I to the 7th is 1 times -I, so that's just going to be -I theta to the 7th over 7 factorial. And then we have I to the 8th, but I to the 8th is I to the 4th times I to the 4th. And I to the 4th is 1. So this is I to the 4th times I to the 4th, or just 1 times 1, which is 1. So we have 1 times theta to the 8th over 8 theta. And we have I to the 9th, which is I to the 8th times I, and I to the 8th was 1. So I to the 9th is 1 times I, or just I, theta to the 9th over 9 factorial. And then I to the 10th, this is I to the 8th times I squared. And remember, I to the 8th is just 1, and I squared is -1. So this is +1 times -1. So we get negative theta to the 10th over 10 factorial. And again, another ETC, good grief. And I guess I'm going to have to clear up some room here. We're continuing from this line up here, just because we're short of blackboard space. And you know what? I'm going to take all of the terms that don't have a factor of I in them and put them together. And then I'm going to take all the terms that do have a factor of I and put them together. Okay, let's see. This doesn't have an I, so that's 1. And let's see, the next term that doesn't have an I is this thing, minus theta squared over 2. The next term that doesn't have an I is this thing, plus theta to the 4th over 4 factorial. And the next thing that doesn't have an I in it is this thing, theta to the 6th over 6 factorial. And then the next term that doesn't have an I in it is this one, theta to the 8th over 8 factorial. And the last term that we have there that doesn't have an I in it is negative theta to the 10th over 10 factorial. Let's see, is that how I wanted to do it? Oh my goodness. Oh, let's see. Let me make sure I do this right. 1 minus theta squared over 2 plus theta to the 4th over 4. And see that? I missed a sign. This should be negative theta to the 6th over 6. See that? And then, I missed a sign again, plus theta to the 8th over 8. Okay. I should be shot for that mistake. Thank goodness nobody around here has a gun. So let's see, the last term down here that doesn't have a factor of I is this one, negative theta to the 10th over 10 factorial. And to make everything, well, what the heck. I guess I'll just try to scrunch all of the remaining terms over on that side. Let's see. The terms that do have a factor of I have I times theta. And then the next term that has a factor of I is this one, negative I theta cubed over 3 factorial. And then the next term that does have a factor of I, this one, plus I, theta to the 5th over 5 factorial. The next term that has a factor of I is this one, minus I times theta to the 7th over 7 factorial. And then the last term that I have here that does have an I in it, this one, I times theta to the 9th over 9 factorial. And on we go. Okay. Now, since all of these terms have a factor of I guess what I want to do in the next step is just factor out the common factor, I. I'm going to factor the common factor of I out of these terms. So I have left theta minus theta cubed over 3 factorial plus theta 5 over 5 factorial minus theta to the 7th over 7 factorial plus theta to the 9th over 9 factorial Now, for some reason or other, some flashing light is supposed to go off in my brain. Am I getting it? This looks vaguely familiar. Oh my goodness. This thing is exactly the same as this thing, except up here we have x's instead of thetas. 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8 over x factorial minus x to the 10 over 10 factorial. What we have down here in this set of parentheses is exactly what we have up here with theta playing the role down here that x plays up here. And what is this thing? This entire sum? This entire sum is cosine of x. Well, remember, down here, theta is playing the role that x plays up here. So up here we have cosine of x. That means that this expression is cosine of theta. Son of a gun. And by the way, I'm going to make a comparison with what's in this set of parentheses with what's up here. And I realized, let's see, I have plus minus, plus minus, plus minus. That should have been a minus sign. Just so that we'll know to correct it, I'm going to write it in red here so that we'll know that this is correct, but the plus sign that I had here before was incorrect. Now, let's look at what's in this set of parentheses and compare it with what we have up here. And down here we have theta. Up here we have x. Down here we have negative theta cubed over x 3 factorial. Up here we have negative x cubed over 3 factorial. Down here we have theta to the 5th over 5 factorial. Up here we have x to the 5th over 5 factorial. Down here we have negative theta to the 7th over 7 factorial. Up here we have x to the 7th over 7 factorial. And down here, theta to the 9th over 9 factorial. And up here, x to the 9th over 9 factorial. Son of a gun. The only difference between what I have up here and what I have in the parentheses down here is that down here, theta is playing the role that x plays up here in this expression. Every place up here that we have an x, we see theta down here. And what is this expression? X minus x cubed over 3 factorial, etc. This is sine of x. Well, the only difference between this and this is that down here, theta is playing the role that x plays up here, and this is sine of x. So the expression in the parentheses down here must be sine of theta. So the expression in the parentheses down here is sine of theta. And don't forget what we have out here. We have this I times everything inside the set of parentheses. So this is I sine of theta. Now, how did we get this gobbledygook in the first place? We started out with the Taylor series expansion for e to the I theta. And this is what it equals. It equals this plus that. In other words, e to the I theta is equal to cosine theta plus I sine of theta. That's huge. And we're going to write that result down. And then we're going to look at some things that show that this result is perfectly consistent with things that we already know. So right at the top, I am going to summarize our results. So let's say that we're representing a complex number in polar form. The modulus of the number times cosine theta plus I sine of theta. Well, see, cosine of theta plus I sine of theta, that's e to the I theta. Now, let's see where all of this jives with stuff that we already know. What happens if we raise a complex number to a power? Let's say n. Well, we have the modulus to the nth power, and the original angle is multiplied by n. So in polar form, this is what we get when we raise a complex number to a power. Now, what happens when we raise this thing to the nth power? Well, we have a product, r times e to some power. And when we have a product raised to a power, doesn't the exponent distribute to each factor? So this is going to be r to the n times e to the I theta to the n. Now, if we have something raised to a power, and that whole thing is raised to a power, what do the exponents do? Don't they multiply? So we're going to get this exponent times that exponent. We're going to get e to the I n theta. Now, does that jive? Let's see. This is what we know. In polar form, we're going to get r to the n times cosine of n theta plus I sine of n theta and that's going to be equal to this thing. Which is exactly what it should be. R to the cosine of an angle plus I sine of the same angle is I'll tell you what, let me be more general. A magnitude, R, times cosine of an angle plus I sine of an angle is equal to R times e to the power of I times that angle. Well, again, here we have a magnitude, r to the n, times cosine plus I sine of an angle. The angle is n theta. And what do we get? We get the magnitude times e to the power of I times that angle. See? Whatever is up here goes up there. Whatever is down here appears up there. Check. And the modulus is the same. So this is consistent with what we know about raising a complex number to a power. In polar form, we raise the modulus to the power, and we multiply the angle by n. In exponential form, we raise the modulus to the power and multiply the angle by n. Perfectly consistent with what we already know. Now, let's look at another example just to convince ourselves that these two things being equal is perfectly consistent in both forms of notation. And you know what? I need to have subscripts for my angles, don't I? Theta 1, theta 1, theta 1, theta 2, theta 2. Okay, we're assuming that this identity holds. If r cosine theta I sine theta equals r e to the I theta, then we can represent Z1 and C2 two different ways. Let's see what happens if we multiply these things together. Whoops. Nope, not plus here. We're not adding, we're multiplying. Okay, we know how this works out. We take the moduli, R1 and R2, and we multiply them together. And the angles add. So we get cosine theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Now, if we use this form of notation, the same kind of thing should happen. So I'll write equivalently and we'll get R1 e to the I theta 1 times R2 e to the I theta 2. And let me redo these subscripts here. I murdered them. Well, multiplication is commutative, isn't it? So can't I rearrange the order of the factors? And I'll put the r's first, R1, R2. And I'll put the exponential second, e to the I theta sub 1 times e to the I theta sub 2. We have a common base, e. We have a common base raised to two different powers. So what do the exponents do? They add, don't they? So we're going to get e to the I theta 1 plus I theta 2. Oh, and this sum has a common factor of I. So I can factor that I out and say e to the power of I times theta 1 plus theta 2. And notice what we get. This thing is exactly equal to this thing. Exponentiation works. Exponentiation works with this form of notation. And it works with this form of notation. And I said exponentiation. Yeah, that's right. Take z and raise it to a power. It works the same with this form of notation as it does with this form of notation. We just raise the modulus to the power and multiply the angles by the exponent. Multiplication works with this form the same way that it works with this form. We take the product. See, we have this thing times this thing. We take the product of the two moduli, and then we have the cosine of the sum of two angles plus I times the sine of the sum of two angles, which is exactly the same as this. The product of the two moduli and e to the power of I times the sum of two angles. If we divide, are we going to get the same thing? Yep, absolutely. What the heck, we're on a roll. Let's go ahead and do it. Cosine theta 1 plus I sine theta 1. Okay. And that's equal to R1 e to the I theta 1. Z2 is R2 cosine theta 2 plus I times sine theta 2. And writing it in exponential notation, it's R2 e to the I times theta 2. And things should work out regardless of which form of notation we use. We should get the quotient of the moduli, and it should be multiplied times the cosine of the difference of the angles plus I times the difference of the angles, or the quotient of the moduli times e to the power of I times the first minus the second. Let's just do this and make sure that we do. Make sure we get exactly what we should get. So let's see, we're supposed to get R1 over R2, the quotient of the moduli, and we're supposed to get cosine of an angle plus I times sine of an angle. And what is the angle in both cases? Isn't it the angle of the numerator minus the angle of the denominator? So theta sub 1 minus theta sub 2, theta sub 1 minus theta sub 2, let's see. We can split this up into the product of two things and say this is R1 over R2 times e to the I theta 1 over e to the I theta 2 . So we have R1 over R2. And now we have a common base, e, and we have e to one power in the numerator, e to another power in the denominator. So don't we subtract exponents? The exponent of the numerator minus the exponent of the denominator. And we have this common factor of I again, so we'll factor that out. We factor the common factor I out, and we get theta 1 minus theta 2. And again, this works out exactly as it should. We get the quotient of the moduli, R1 over R2. And here we get cosine plus I sine of theta 1 minus theta 2. Here we get e to the power of I times the difference of the angles, theta 1 minus theta 2. So these forms of notation are equivalent. And algebraically, when we do multiplication, exponentiation, division, they work analogously. Essentially what we do, we take the, for division, we take the quotient of the moduli, excuse me, and the difference of the two angles. quotient of the moduli, and the difference of the two angles. So in exponentiation, multiplication, and division, things work analogously in both forms. Now there's one thing that we haven't addressed yet, and it's a logical consequence of what we've already done. And we'll look at that in just a second. I think I need to blow my nose. Boy, what a lame excuse for a pause, huh? But I have to do it. Okay, I'm very much relieved now. We can get back to work. And one thing that we want to remember, if we have a complex number z equals r times cosine theta I sine theta, this number, nth root of the real number r, times cosine of theta over n plus I sine theta over n, is an nth root of z. In other words, if we raise this thing to the nth power, we get z. So I guess the first thing we want to investigate is whether that same thing holds for the exponential form of representing a complex number. Whoops, 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 whoops. Does it work? Essentially, this number is equal to that number. It has the same modulus, r to the 1 over n. And we have cosine plus I sine of the same angle. We have cosine plus I sine of theta over n. And we have e to the power of I theta over n. So this should be an nth root of z, because this is supposed to be an equivalent form of this number. Well, how would we show that this thing is an nth root of z? Well, by definition, an nth root of z is any number that we can raise to the nth power and get z. So let's do that. We'll answer in the affirmative and then say, observe. We take this number and raise it to the nth power. And what we have is a product. R to the 1 over n is one factor, and e to the power of I theta over n is another factor. We have a product raised to a power. So we can raise each of these separately to that power. Or looking at it another way, the exponent distributes to each factor of the product. So we have r to the 1 over n raised to the n times e to the I times theta over n raised to the n. We have something raised to a power, in turn raised to a power. What do the exponents do? That's right, they multiply. So we get r to the 1 over n times n. And then we get, same thing here. Something raised to a power. That whole thing raised to a power. Those exponents are going to multiply too. So we get e to the theta over n, that whole exponent times n. And so that's going to be r to the first times e to the I times theta. See, r times e to the I to the theta. R times e to the power of I to the theta. That was z, wasn't it? So what did we establish? R to the 1 over n, e to the I theta over n, raised to the nth power equals z. So r to the 1 over n, e to the I theta over n is an nth root of z. Now we expect for there to be how many nth roots of a complex number? N? So let's see if we can carry this a little bit further. Okay, I think this might be our last installment with showing that the exponential notation works exactly like the polar coordinate notation. The analog between the two is perfect. Now remember this, if we have a complex number, z equals r cosine theta plus I sine theta, the nth roots, the entire set of nth roots of z are given by this formula. The nth root of r times the cosine of theta plus 2k pi over n. Now remember, plus I sine theta plus 2k pi over n. Remember we showed just a minute ago that r to the 1 over n cosine of theta over n plus I sine theta over n was an nth root of z. What we're showing now is that if we add this 2k pi to the numerator, we get the entire set of nth roots. And if the exponential notation is perfectly consistent with the polar notation, then we can replace r to the 1 over n with r to the 1 over n. And we can replace cosine of, we can replace cosine plus I sine of theta plus 2k pi over n with e to the power of I times that same angle, theta plus 2k pi over n, for k equals 0, 1, 2, 3, all the way up to n minus 1. So what we want to do is show that for any and all values k from 0 to n minus 1, this thing is the nth root of z. So first of all, we'll attack this problem or this exercise by answering in the affirmative, yes, that this does give the entire set of nth roots. And notice that for each value of k, from k equals 0 to n minus 1, we get a distinct nth root. So if we let k run through all of its values, all of its n values from 0 to n minus 1, these values of k generate all of the nth roots of z. So first we answer in the affirmative that this does yield all of the nth roots. and that everything that this formula gives us, in other words, the value of this for every value of k, is an nth root of z. Now let's see, how are we going to do this? And what am I doing here? I'm reasoning that if for any value of k from 0 to n minus 1, this really is an nth root of z, then if I raise this to the nth power, I get z, because that's what an nth root is, isn't it? It's a number that we raise to the nth power to get z. So I'm going to take this, raise it to the nth power, and show that no matter what value k is, from 0 to n minus 1, we're going to get z. And first we notice we have a product. We have r to the power of 1 over n times e to the power of I times garbage. So we have a product, this thing times this thing, raised to the n. The exponent will distribute to both of these factors. And we'll get r to the 1 over n to the n power. And we'll get e to the power of I times theta plus 2k pi over n to the n power. Looks good so far. We have something raised to a power, that whole thing raised to a power, the exponents multiply. So we get r to the power of 1 over n times n. And we get e to the power of I garbage over n to the power of n. These exponents multiply as well. Well, n times n, they cancel. Okay. We'll distribute the I inside the parentheses. And now we have e to the power of the sum of two things. Then let's see, how can we reason on this? If we have e to the x times y, and maybe I ought to write that bigger. If we have e to the power of x times y, no. Maybe we ought to write it correctly. Okay. If we have e to the x times e to the y, can't we write that as e to the power of x plus y? The exponents add, right? Well, equations are a two-way street. Not only do they go from left to right, which is usually how we think of them because we read left to right, but equations also go from right to left. So we have e to the power of the sum of two things is equal to e to the power of the first times e to the power of the second. And that tells us exactly how to write this. We have e to the power of the sum of two things. So we write it as e to the power of the first times e to the power of the second. And now what do I do? Supposedly, e to the I 2k pi, that's equal to cosine of theta. No, it's equal to cosine of this angle, 2k pi, plus I sine 2k pi and k is a whole number. K is 0, k is 1, k is 2. K is a whole number. So the sine of any whole number multiple of 2 pi is what? Let's see, sine of 0 pi is sine of 0, which is 0. Sine of 2 pi is 0. Sine of 2 times 2 pi, or 4 pi, is 0. All of these guys are 0. And cosine of 2k pi for all whole number values of k, and k is just whole numbers. Let's see, cosine of 0 is 1. Cosine of 2 pi is 1. Cosine of 2 times 2 pi is 1. For all whole numbers k, cosine of 2 pi is equal to 1. Well, this is what we started with, isn't it? We took this thing, raised it to the nth power, and we got r times e to the I theta, or z. So, for all n values of k, this expression is a number such that when we raise it to the nth power, we get z. So we can say that that is the nth root, or maybe more correctly, so this exponential form of representing a complex number is very much analogous to the polar form for representing a complex number. All of the operations are analogous between the polar form and the exponential form, and that includes multiplication, division, exponentiation, and nth roots. So, a way to represent any complex number, r times e to the I theta. The algebra works very well for multiplication, division, exponentiation, nth roots. It works just as easily, if not more easily, than the polar notation. So this is something that we want to be very familiar with.